Coming to master orchestrator, it takes 3 parameters. First one is source name. Then it takes 2 flags. One is associated with the first load and second one is associated with the selective restart of failed jobs. Enabling this flag will rerun only the failed jobs from the previous run. Let us dive into the batch generation logic. It is implemented in a stored procedure and it takes in 2 input. One is first load flag and the source name. The output of this stored procedure is an batch execution date and the previous run status information. So the previous run status information can be either failed or success. Let us understand the logic for generating the execution date. Entire logic is captured as a flowchart in the GitHub page. By clicking on this link, you can view the flowchart. The stored procedure logic start with by checking the first load flag. If the first load flag is true, a new batch execution date is generated with this current timestamp format and the previous run status is set to true. If the first load flag is false, then the stored procedure look into the test pipeline control table for the number of failed tables from the previous run. If there are any failed tables from the previous run, then the previously generated batch execution date is reused and the previous run status will be set to failed. If there are no failed tables in the test pipeline control table, then a new batch execution date is generated and the previous run status is set to success. The next step is to identify the list of objects that needs to be ingested. This list can be the list of failed tables from the previous run, or it can be all the tables associated with the source. This step takes 3 parameters as input. One is the previous run status information. This previous run status information is provided by the first step. Then next one is retry failed flag. The retry failed flag is an indicator that determines whether to retrieve the failed tables from the previous run. Then it takes the source name as parameter. The entire logic is implemented again in the stored procedure and it is captured as a flowchart in the GitHub page. And logic start by checking the previous run status information. If the previous run status information is failed and the retry failed flag is set to true, then the stored procedure return all the failed tables from the previous run. If the retry failed flag is set to false, then the table returns all the table associated with the source. Next step is about triggering the parser logic pipeline for each table. From a technical perspective, a master orchestrator uses lookup activity for batch execution date generation, and also for identifying the number of tables that needs to be ingested. Here the lookup activity can be replaced with a script activity. One thing to note here is the limitation associated with this activity. Lookup activity has a limitation of around 2 MB of data or 4K records, and for script activity this is around 4 MB of data. For script activity, this limitation can be overcome by enabling logging feature in the advanced section of the activity. Now let us move on to our second pipeline, that is config parser pipeline. Config parser pipeline start with reading the configuration specific to the table from the control table. The control table here is test metadata control table, and the configuration is specific to the table. Next we have the logic for computing the last successful execution date. last successful execution date is used by the incremental load to identify the delta record. So first we check for the first load flag value. If the first load flag is false, the last successful execution date is computed from the test pipeline control table. When a new table is added to the already configured sources, the test pipeline control table will not have an entry for this newly added table. Consequently, the last successful execution date computed for this specific table is -1. This indicates the framework to pull all the data from the source. When the first load flag is true, the last successful execution date that is returned is -1. Next, we have a switch activity that identifies whether the ingestion is incremental or full load based on the configuration mentioned in the test metadata control table. So the configuration that is specific to the incremental load is data loading behavior under the configuration table. Next step captures the status of the data ingestion pipeline. For a successful run, the last successful execution date value is the current pipeline execution date, which means that for a successful run, the batch execution column and the last successful execution column of test pipeline run table is same. In case of failure, the last successful execution date column in the test pipeline control takes value from this specific variable. This variable stores the last successful execution date, which is computed as the second step in this pipeline. It can take one of the two values depending on the type of run. For the first load, it is -1, and for a subsequent run, it is the previous successful run's batch execution date. So just to summarize, in case of failure for a first load run, the last successful execution date column will have -1, and if the failure occur during the subsequent run, then the last successful execution column will have the previous successful run's batch execution date. Now let us run the pipeline for a source named source 1. Before running the pipeline, let us look into the configuration for the source 1. So for source 1, we have two tables. One is an incremental table, which I have suffixed with INCR. Another is the original table. So let's examine the configuration. So here we are mentioning the source details, the sync setting. One is related to the cloud storage information. Another is related to the staging table related information. So here we are having a staging schema. Then we are mentioning the target schema and the target table name. Another thing is data loading behavior setting. Here the data loading behavior, it will have INCR, which stands for incremental, and the offset and the primary keys are mentioned. For a full load table, we don't have only the load data loading behavior is full. Other than that, all the other fields are not mentioned. Then this is the first time we are going to run this pipeline. So I have cleared the control table that capture the run status for the pipeline. So we don't have any data. Now let us see the number of records that are there in the source. So source table has the full load has 7 records and incremental has around 16 records. After the successful ingestion, these should be the number of records at the target table. Now let us trigger the pipeline. So I am mentioning the source name. I am setting the first load flag to true, which is T. in triggering it. Pipeline has been triggered, and this is a master pipeline. It has triggered two configuration pipeline, one for full load and another one for incremental load. So let's see. Yeah, you can see the incremental as well as the full load pipeline. You can see the pipeline has successfully completed. So let us look in. Let us examine the pipeline once. So you can let us look into the execution date which was generated. It is 2024/6. So this is the, as the pipeline is successfully completed, this execution date and the last successfully completed execution date should be same in our control table. In the JDBC config parser, you can see the last successful execution date is set to -1, as there is no run history for this source. So let us examine the control table, what run status control table, what are being populated in that. So you have a success status and the execution as the completion ingestion is completed successfully. The execution date and the last successful execution date are same. Now let us move into the incremental pipeline and the full load JDBC pipeline. The incremental pipeline, let us see the number of records that are read from the source under incremental JDBC. It says 16 records are read. So it again matches with our source record count. For full load, it should be 7 records. Let us confirm it once. So 7 records are being read. Next, validate the target table record count. Starting with the full load table, you can see around 7 records are being ingested. Compared to source table, there are 2 new columns that are added to the target table. One is row extract DTTM, another is batch execution date. Row extract DTTM is the current timestamp and batch execution date is the execution date that is generated by the master orchestrator. Moving to the incremental load, again our record count is matching with the source. Now let us examine the incremental pipeline. Number of records read here is 16. This is again matching with the source table record count. If you observe the logic to combine the stage table and the target table, it is noted that the merge logic is not triggered. This is because our current run is a first load. The logic block that is triggered is a drop and create, wherein all the data from the stage table will be copied to the target table. Now let me prepare the data for the subsequent run. So I have my inserts ready. I'm going to change. I'm going to have one insert and another one update. So I'm going to add a new project. Then I'm going to update the project to 1. So it is successfully updated. Let's examine the number of records at the source. Here I am sorting the record based on the descending order of the creation time column. Here we have total of 17 records, of which 2 of the records have the latest timestamp. Before running the pipeline, let's verify the incremental read logic. This is the logic that is used in the pipeline to identify the delta records. It takes last successful execution date as the parameter. You can obtain the last successful execution date from the test pipeline run control table. Copy the date from here. Replace this date with the last successful execution date. Now let's run this logic. This now returned 2 records. This is actually the records that are modified at the source. Now let's trigger the pipeline and verify the number of records. The subsequent run has been triggered. Let us wait for it to complete. The pipeline is successfully completed. Let us see the number of records that are read from the source as a part of incremental load. It should be 2 records that has to be read. Yes, it is 2 records, and there should be only 1 record that should be added at the source. So again, let us see the status of let us see the control table that track the status of the run. So we have 2 new entries in the control table, and the execution date are added. Let us validate the record, that is number of records at the target. So you have 2 batch execution date. Let me sort it descending order. So for 12/9/18 you see there are 2 records. One is project 1, that is the record that is being updated, and this is the newly added record. Now let us examine the steps involved in installing and configuring this framework. Start by downloading the code available in this repo. All the artifacts related to ADF pipeline or our ingestion framework is available under this folder ADF code. Once imported, navigate to the pipeline folder, where you will see a folder starting with MDDI. This folder contains all the pipelines used by the framework. There are 2 pipelines that are ending with master, which are used for testing the corresponding ingestion pipeline. So full load JDBC SQL master is used for triggering the child pipeline, full load JDBC SQL child pipeline. Before we proceed further, let us quickly recap the components of an ADF pipeline. An ADF pipeline is a logical group of activities. So each activity interact with the data sources using data set and linked services. The linked services are like the connection strings to the data sources. Say for example, for an Azure SQL DB, the linked service is the credentials, login credentials information. Coming to dataset, these datasets represent the data source that the pipeline will be connecting to. The dataset can have information related to the object it has to connect. Say for example, for a JDBC source, a dataset can have the source, have the table name and the database name. For a cloud storage, it will have the storage account and the location of the object. Now let us examine the datasets used in the framework. All the dataset used by the framework is grouped under a single folder, MDDI_version01. First one is to connect to the source and target table. The source and target table in our case is Azure SQL DB. Next, we have the linked service that connects the dataset to the Azure SQL DB. There is a naming convention that is followed throughout the framework. For linked service, all the linked service starts with ls underscore, and the dataset starts with ds underscore, and for pipeline it is pl underscore. Now coming to the linked service, the linked service here is parameterized. The parameters are related to the connection details and the authentication information. Moving to the second data set, it represents the control table. Here we are not using a parameterized linked service to connect to the control table. This is basically to reduce the complexity. Now coming to the third data set, this data set represents the Azure storage account. again, the linked service that is used here is parameterized. Here the storage account is parameterized, and again the data set takes parameters that identifies the location of the object in the storage account. Next step is to create the control table. The DDLs are available under this link. These are the DDLs used to create the control table. SQL used file has all the stored procedure logics, the sample configurations used, and the JSON manipulation samples are also available under this file. Next step is to prepare the configuration. Again, the sample configuration is available in the README file as well as in the SQL used file. Now let us look into the limitation of the framework. The first limitation is about the metadata table. If the configuration is stored in a SQL Server database, the version of SQL Server must support JSON manipulation. This requirement also applies to any JDBC source that store this configuration. Second limitation is about the watermark column. Currently, the framework support watermark column of timestamp data type. The copy data tool provided by ADF supports identity or automatically increment value generation columns. You can overcome this limitation by using the similar approach used by copy data tool. In copy data tool, after each successful execution, the watermark column max is computed and captured in the configuration table. So the similar logic can be implemented here. One suggestion here is to use this calculated computed value or the runtime information in a separate table rather than clubbing it with the configuration table. Moving to the next limitation, the framework cannot be parameterized for no JDBC source, which means if your source is Oracle, then the framework needs to be modified to include the new link service datasets, all those pointing to the Oracle. Another limitation is schema evaluation is not addressed while developing the framework. Again, this is a food for thought. It needs to be thought and implemented. So these are the limitations which I can think of. There are a couple of things which I have learned as a part of building this data ingestion framework. So again, these are captured as a markdown file under the same GitHub page. So going to lessons learned. The initial idea was to use data flow for data ingestion, leveraging the Spark capability for ingesting data from any kind of source. But what I understood is that the data flow cannot work on a self-hosted integrator runtime. And again, the Azure recommended approach is to use a self-hosted integrator runtime if your source is residing in an on-premise network. If the source is in an on-premise network, and again, if you want to use a data flow, you have to use copy activity to bring the data into the cloud storage. Then only you can use a data flow for further processing. So the reason I have decided to go with the copy activity for my entire data ingestion framework. Next is about the global parameter. My initial assumption was global parameters are similar to Airflow variables, where it is easy to, in Airflow, it is easy to edit or update the variable. Idea is to capture this execution date in a global parameter, and this global parameter will needs to be updated at the end of each batch execution. Unfortunately, could not find any option to modify this global parameter at runtime. So decided to capture this parameter in a control table and modify it using a stored procedure. Next, let's talk about the stored procedure activity in Azure ADF. It is important to note that the stored procedure activity in ADF does not work with stored procedures that returns value. However, there is a workaround. The workaround is to use lookup or script activity instead. The detailed implementation of this approach is mentioned in the reference URL that is mentioned here. In the current framework, either for a full node or an incremental node, we are kind of reading the entire data. Okay, we are not using a query-based approach to extract the data from source. So it is better to use a query-based approach. The reason for that, you can have a control over the number of columns that needs to be extracted from the source. So to implement a query-based approach, there are two things that has to be done from this data ingestion framework. First thing is you have to pass the query here to this field, and again the copy activity has to be modified to include this read from this field. Next pointer is about the idempotency of the framework. Idempotency means here the multiple run of the data ingestion framework with the same batch execution date should not create multiple files under the same target location. To prevent this issue, the target location should be cleaned before each run. Ideally, the copy activity in the ADF should have an option to delete the file before writing it into the target location. But there is no such built-in feature for a file-based sync. What I have observed is that for a JDBC sync, there is an option to run a script before writing to the sync. So this can be leveraged for cleaning the table before writing. There can be two solutions to achieve this feature. So first one is to introduce a delete activity before ingesting the file, which will clean the sync location before writing to the target. Another approach that is implemented in the framework is to specify the target table name in the file name field under the sync configuration of the copy activity. This approach ensures that there is only a single file that is created in the cloud storage location with the file name that is matching with the target table name. In case the pipeline is re-triggered with the same batch execution date, it will not create new files but will instead override the existing file at the target location. And this is another thing, for each activity which has execute pipeline in debug mode does not run parallelly. In copy activity, we have a feature to add additional columns. This pointer is about the restartability of the copy activity. Like I mentioned earlier, the key requirement for the framework is to support a selective rerun of the failed jobs. This is not supported in copy activity, so we have handled it using a custom logic. There is an option to manually restart the failed pipeline that is done that can be done through UI. Let me show you that. Under the monitor tab, you can select the failed pipeline and click on retrigger. In addition to this, I have also compiled notes related to various ADF activities, and there are reference link mentioned for certain notes. This page will be regularly updated based on my ongoing project experience.